We're going to do now more conformational analysis of disubstituted cyclohexane, this time with a different pattern. See that the problem that we're having a problem on a test or a homework or something, and it says to draw the more stable conformation of the following compound, and it gives you this. Now I'm going to put a bromine here, and now I am going to here say up and down. So say that the problem asks you to draw the more stable conformation of these two compounds. Okay, so now let's look at what is a pattern for the substitution. Notice that here I have relative to each other. This is 1, 2, 3. It is a 1,3 disubstituted cyclohexane, and this is also 1, 2, 3. But notice that here in the compound on this side, the pattern is up, metal is up, bromine is up. Here, metal is up, bromine is down. Now let's draw the chairs. I'm going to draw the first one here. Remember that when we said this up, this also has a name. This is a cis disubstituted because they're pointing to the same side. This is opposite sides, so that is the trans. That's the number. Now let's draw the chairs. I'm going over to the cis first, and I'm looking at this little model to remind us where the axial and equatorials are. The axials are the vertical lines, and the equatorials are slightly tilted relative to the center. So let's draw the C's here. So I say it's 1, 3, remember. So say that I have a metal here up, right? And this is carbon 1, 2, and now in carbon 3, I need to put the bromine up, see? So it needs to be here. Say again, if the metal is up, now we count 1, 2, 3, and the bromine is also up, and I'm looking at this drawing. If the metal is here to be up, it needs to be axial, like looking at this drawing here. And so now I have that, and let's do the chair, the flip. So this corner that is down, I'm gonna draw up, and this corner up is going to go down. What is axial here will go equatorial. That's my carbon 1, 2, and 3. And here what is axial is going to go equatorial. So now doing the analysis of which of these conformations is more stable. So let's see here. We have two substituents, axial, axial. And here in the chair flip, we have the two substituents, equatorial, equatorial. So clearly, this is much more stable because we don't have the 1,3 diaxial interaction. So equilibrium is shifted to that side. So this is the case for the C's. Now I am going to do the same analysis for the trans. So I'm gonna just divide the screen like so. Doing the trans here. Okay, making this bolder. Now, we said metal up, right? I'm going to draw it here. To start with something, right? So 1, 2, and 3, but now it says the bromine is down. Notice that in this position, bromine up was axial. Now bromine down will be here, equatorial. So that's one of the chair, up, down, notice. In the chair, the flip, they still need to be trans, so up, down. Notice that this is up, up, so still is cis. And you should be checking what you're doing when you do the ring flip. Here is up, up, so still cis. The relationship here of the two substituents still is trans, so up, down, and it should be the same in the flip. So now what was axial goes equatorial. And if you count 1, 2, 3, that's where the other substituent goes. But it was equatorial, it will go now axial. So that's your bromine atom. And this is 1, 2, and 3. Notice here I am omitting the other positions not to have it too crowded. But now let's do the analysis and see which of these will be more stable. In the trans, this is the 2 chairs for the trans, right? In the trans here, I have 1 substituent in this conformation, axial. Bromine is in equatorial. When I do the flip, this is now equatorial, this is axial. These two have about the same energy. What is different is that now 1 substituent is a metal and the other is a bromine. So now what side will be preferred just depends on the size. So if you think if bromine is larger than a metal, then the preferred conformation will have bromine in equatorial. But let's say that we want to make it more dramatic. I'm going to do another exercise with even bulkier groups so that you see that better. So let's do that in another video.